Okay, so you remember conservation of energy and how we had a left side and a right side, initials and finals. Well, we do have something called conservation of momentum. And recall that momentum is mass times velocity. So this is for two objects. And they don't have to be the same mass. They can definitely be different masses. So we have an M1, and the M1 is not going to change its velocity, its mass. Neither is M2. So even though we do have different masses, we're going to assume that the mass doesn't change itself. So if M1, for example, is 100 here, 100 kilograms, then it'll be 100 kilograms with the final velocity. So on the left side, we have all the initials. On the right side, we have all the finals. And that is conservation of momentum. Now, for the record, this is conservation of linear momentum. And yes, we can do angles as well. We may look at some of those in the future. However, the AP test doesn't really test angles heavily when it comes to momentum. So, one big thing to keep track is that when we draw our velocity vectors, we want to make sure that our signs are implying the direction that the object is traveling. And we should also not just draw one drawing, but draw a few drawings to see the before, the during, and the after the collision. So this is going to be a focus. Usually when we talk about conservation of momentum, linear momentum, we're also focusing on different types of collisions. So let's draw a few things. Let's do A. Object A and B are traveling in the same direction. So let's say here's A, and let's say here's B. And here's a velocity vector going in this direction and going in this direction. So because they're both going in the same direction, I'm going to make going to the right be positive because it's convenient. I want to make one be negative, one be positive because they're both going in the same direction. Object A travels towards object B, which is at rest. So this has an initial velocity of 0. This has a velocity, so I want to make going to the right be positive in this case. Object A and B are traveling towards each other and they will collide. So I can make this positive and I can make this negative. Or I can switch them around if you'd like. Regardless, we need to make sure that they're oppositely signed. Now, a couple of things might happen here. They may either cancel each other out when they actually collide. They may switch velocities, or they may do some other weirdness with it. So there are three types of collisions, linear collisions. The first is elastic, and this is ideal. Like this in real life, this only happens at the atomic level. Imagine, if you will, holding a basketball at your shoulder length, with your arm outstretched, and you release a basketball. You don't push on it. You just release it from rest. Imagine instead of it, after the bounce, it actually comes back directly to your hand. Now, we know in real life that doesn't happen, right? In real life, that's actually inelastic collision. So when I go ahead and hold the ball outstretched and I release it, it hits the ground and it bounces back a bit, but it doesn't come back all the way because it lost some of the energy. And after each successive bounce, it gets closer and closer to the ground. Elastic collision would be where if I release this ball, it would hit the ground, bounce, come back to my hand, and it would just do this forever, perpetually. Okay. Now, I mentioned that in real life, atomic particles do this because they're bouncing off of the walls even as I'm speaking right now. That's why you can hear my voice. We sometimes see elastic collisions in real life when we play pool. With the red and blue balls and the black cue ball and the white ball and all that kind of stuff. Sorry, did I just say the black cue ball? But you have sometimes one ball hits another ball that's stationary, and they actually switch velocities. Because they happen to be the same mass, they actually end up switching their momentums. So one is moving, the other one is still, and then it hits it, and then they switch off. That's an example of elastic. Elastic collisions, the momentum is conserved and the kinetic energy is conserved. Now, momentum, you already saw the formula for that. For kinetic energy, let me give you just a sneak peek and skip a bunch of algebra and kind of give you something that the cheat sheet on College Board doesn't give you, something that you can remember easily. So this only works for elastic collisions, But if I need, for elastic collisions, these are the harder problems, because in order to solve these problems, you have to set up conservation of momentum and you have to set up conservation of energy. And that means you need to set up two equations. Now, we showed you what momentum looks like. Energy, conservation of energy for elastic collisions looks like this. It's going to be V1 initial plus V1 final is equal to V2 initial plus V2 final. It may seem counterintuitive conceptually. I've skipped a lot of math for you. This is easy to memorize, so just use this, okay? And somehow the masses are going to cancel out magically, even if the masses aren't the same. Not going to even go there. Just take it for what it is. We talked about inelastic collisions. That's where momentum is conserved, but energy isn't. So this is a lot more like real life. Okay, I throw a ball at the wall, it bounces back, but doesn't come back all the way to me. The reason why when you dribble with basketball, you have to add more of a force when you push it down. That way you're guaranteeing that it comes back up. If you simply just released the ball, it would not come up. And so you have to add that additional force that you never thought about until now. But when you dribble, you have to kind of pump it up and prime it up and almost be hitting. You're almost slapping the ball back to the ground. You're giving it that much additional energy to compensate for the energy that was lost in the bounce because it was not conserved. Every time you hear the ball bounce, you're hearing the effects of a loss of energy. We talked about it when we talked about energy, how that was a heat energy loss. You also have sound, which is a byproduct of energy loss. And so as a result, you're going to get less energy going back up and less potential energy coming back up as well. So regardless, inelastic is more real life stuff. Okay. There is a very special case, which is called perfectly inelastic collisions. And this is a special case of inelastic, right? Momentum is conserved, but kinetic energy is not. Check. However, the two objects stick together after the collision. And this is convenient because if they stick together after the collision, they have the same final velocity because they're one big chunk. Okay? So, unfortunately, automobile accidents, if you see these, if you see one car mangle into another car or a motorcycle, then that's two separate masses that became one mass, and they had a final velocity because they were one giant mass. Okay? These tend to be our easier ones, relatively speaking. And personally, I like perfectly inelastic because you have less variables to deal with. You have the same final velocity. So let's do a couple of examples. Okay, I'm going to need a lot more room for this one. So here we go. We have two billiard balls, so pool table, right? And lucky for us, they happen to have the identical mass. Okay, now I'm going to show you what that means here in a bit. But they're moving towards each other. So check it. We have... this is the before, right? They're heading towards each other. And then during the collision, they actually touch and hit. And after the collision, what do we expect? Well, it depends on these velocities. We could expect that they're either moving towards the right together or to the left together, or maybe in this case, they'll go in opposite directions. Okay, so this is your before. This is during, and this is after the collisions. Now, they did give us some velocities. The one ball has a positive 30 centimeters, and the other one's got a negative 20. So they already labeled it for us. That's very nice. Okay. Now, it sounds like, okay, they're perfectly elastic. This is elastic. This is elastic. Great. So what this means is if it's elastic, then we know that energy is conserved. So what I drew for the after is very much true. Now, conceptually speaking, we have a very special case going on here that I'm going to show you a surprise at the end. But we can expect that these guys are going to switch energies. Okay, so they're going to hit, and then this is going to go away, and this one's going to go away because it's elastic. Now, if it was perfectly inelastic, then they would be going off together as a pair. Okay, let's go ahead and set up a few things. We'll set up the conservation of mom. Yeah. And that's going to be M1 times V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. And they have the same mass, so that means M1 is M2. And if that's the case, well, they could all just cancel out because they're in this case they're identical. Don't cancel them out unless if they're identical. If you have a problem where they're not the same, which we're going to do one next where they're not the same, then don't cancel them out. But in this case, because they're all the same, I'm canceling them out. Okay? So conservation of momentum quickly becomes essentially conservation of velocity in a weird way. Now let's type in this. Let's write in these numbers that were given. So V1 initial was a 30 centimeters, a positive 30 centimeters second, and I'm going to leave it as that because I'm not going to deal with anything else in this problem. You'll see what I mean in a bit. And then V2 initial was going to be the negative 20. (30 minus 20 is 10. So I have V1 final plus V2 final is equal to 10 centimeters per second. Now that's not very good for us because I have two variables. I don't know what V1 final or V2 final is, and I need to find them both. So I'm going to leave this on the side for now, and we're going to have to create a second formula. Now we know that this is elastic, so that means I can use conservation of energy. And the shortcut that I gave you, if you're interested in a full explanation, it's not even a full explanation, but a pretty decent explanation with some of the math, look at the Survey College textbook 9th edition that we use a lot in this class. And you'll see somewhere, beginning on page 179, an explanation of how they arrived to what they got to. But then they gave it to you a different way, and I'm just getting rid of all the negatives because... yeah. Okay, so anyway, we're going to, conservation of energy according to me was V1 initial plus V1 final is V2 initial plus V2 final. And let's plug in what we know. We know this is 30. And we know that this is a negative 20. Now, if I take this and I rearrange it around, I'm going to get the following. And, you know, you should be able to get to that point, your AP. Now, this is lovely because this tends to happen quite often with these problems. I can go ahead and do some Algebra 1. And you'll see that the V1 finals cancel out. And then this is 1 V2 final plus 1 V2 final is 2 V2 final. And that's going to be equal to 60 centimeters second. And if I divide both sides by 2, I get that V2 final is equal to 30 centimeters per second. Now, if I were to take that and plug it back in to either this equation or this equation, I'm going to get that V1 final is negative 20 centimeters per second. So remember how this was a positive 30 and this was a negative 20 before the collision, and then during the collision they bumped and they pretty much switched the arrows around. And now this one gets the negative 20, and this one gets a positive 30. That's what we're getting right here, right? If this is my 1 and this is my 2, 1, 2, 1, 2, V2 final was 30. Notice, the arrows are very important because what happens is that this is conservation of momentum and conservation of energy. So they switched. It was a perfect switch. Now, mind you, it was only a perfect switch because they're identical masses. Okay, if they're not identical masses, you're not going to get a perfect switch. But this is a perfect switch. And what happens is that this 30 gets transferred over to the second object and it takes it away. And the signs also changed, right? So this used to be a negative 20, so it was going to the left because negative is left. But then all of a sudden, it's going to the right, positive 30. And this one that was going right, positive 30, now is going left, negative 20. It was a nice, perfect switch. This is an example of elastic collisions. This is pretty beefy stuff, but if you're comfortable with your concepts and you're comfortable with some algebra, this is a very, very feasible type of problem. Now for this problem, as we read it, we're picking up on a few more clues here. We have an SUV and we have a compact car, so obviously we have different masses. It's okay. We can have different masses, right? It doesn't, even if it's not elastic or if it is elastic, different masses happens. We have some scientific notation, no big deal. Eastbound is positive, westbound is negative. In other words, going to the right is positive, going to the left is negative. The cars collide head-on, becoming entangled. This is the most important word in this whole problem because this reveals to us the type of collision this is. This is a perfectly inelastic collision where they become mangled and come together. Now, this is nice because that means they have the same final velocity. Let's do some thinking here and just some quick drawing. So I have the big one and I have a small one. Don't worry about making these all factual. SUV, compact car. Great. SUV is going eastbound. I'm going to draw a bigger arrow because it's a bigger velocity, 15. And then this is negative 15. So actually I should draw the same kind of arrow going this way, but it's going the opposite direction. Now, they're going to go ahead and crash. And they're going to go ahead and move on. They're not going to bounce off of each other. They become entangled. Now, my question to you is this. From a conceptual, real-life point of view, is this going to, once they become mangled up, is the mangled up mass going to go to the left, westbound, or to the right, eastbound? Well, you're thinking, think about momentum itself. Momentum is a mass times velocity. They both have the same velocity, essentially, but this one's got the bigger mass. So the SUV is going to, based on Newton's laws, is going to be the one that determines which way this whole thing is going. So this whole thing is then going to be traveling in this direction, but with a smaller velocity now. Okay, so notice that I drew this arrow smaller on purpose. I'm expecting my answer, my velocity answer, to be positive, okay, not negative, and to be a smaller number than 15. So if we had to guess in a multiple choice test, we could easily guess something between 0 and 15. Okay? But it's got to be positive. So keep that in mind as we do the math and we get answers. Let's make a list of what we have. We have the mass of the SUV. We have the mass of the compact car. We have the initial velocities. And the V1 final and the V2 final were the same thing. So they're going to just be the same thing. So we can modify the conservation momentum to look like this. Okay. The left side is as we usually do. The right side, we add up the masses, and that's because they're one entangled mass, right? And they happen to have the same final velocity. So we can find the final velocity by then dividing both sides by m1 plus m2. And if we plug in the right numbers and we're careful with our signs, we're going to get that V final is equal to a positive 3 meters per second, which is eastbound, right? Now, that conforms with what we were expecting. We were expecting a number less than 15, but it had to be positive, and 3 is a pretty realistic answer. That's part A. For part B, let's do a few things just to kind of show you what the heck is happening. So part A would typically be the end of a problem for us. But I want to go deeper into some kinds of questions you may be occasionally asked on the FRQs on the College Board exam. So find the change in the velocity of each car. That's a delta V, right? So the delta V of the SUV, it was the final minus the initial, and that was a negative 12 meters per second. So we saw that, right? We saw a decrease in the velocity of the SUV. The compact car, we had a V final of 3 minus a negative 15, right? V final minus V initial, and then ends up being a positive 18 meters per second. And you think, well, what happened here? Well, what happened is that it was going in one direction, and then it's going the opposite direction. So that's how much velocity had to happen. We had to change the velocity from a negative 15 on the number line to a positive 3 on the number line, and that's a total of 18 spaces. Part C is something that I tend to have my college students do, and I've seen it once on a College Board test. So that's to find the change in the kinetic energy of the system consisting of both cars. So let's talk about the before and after. Before, we had two separate vehicles. We had the SUV and we had the compact car. Now recall the kinetic energy is 1/2 mv squared. So if we go ahead and do that for the SUV, right, with the initials, we get that the initial kinetic energy for the SUV is 202,500 joules. And the compact car, we're going to go ahead and get initial kinetic energy of 101250 joules. And that gives me a total of 303,750 joules. That's before the collision. So that's how much energy was in the system. Remember, it doesn't matter which way things are going in a system. The total kinetic energy is going to be added because 1/2 mv squared. The velocity, even if it's negative, gets squared and therefore becomes positive. So with these two cars heading towards each other, this is how much energy is in this system. Now let's look at the after. So they went ahead and collide, they stick together, we've lost some energy, and so what we have here, again using the 1/2 mv squared, is we have a giant mass. So you have the 1/2, it's the two masses combined, and the final velocity is 3. And if you put that in a calculator, you get 12150 joules. Now, look at how much energy we have, but look at how much energy we had. Okay? So, just to give you like a percentage comparison here, if you were to take this amount, actually, let's not do that yet. Let's answer the question. The change in kinetic energy. So if I subtract these two numbers, I'm going to get the change in kinetic energy to be 291,600 joules. That's how much energy was lost because of the collision. Now, to go back to what I was going to tell you here in a moment ago, if you take this number and divide it by this number, you're going to get 0.04, which means, if I move the two spots over, we only have 4% left of the original energy. We lost 96% of the energy in the collision. Okay, where does that energy go? It goes to the destruction of the cars, them becoming mangled, human, hurt, other casualties. So just to put this all into perspective, this is what we started with. This is how much energy was in the system. This is how much energy we have afterwards. This is how much energy was lost. And so we have 96% loss and only 4% energy recovered at the end. And this is why, 4% means the cars are going to be moving forward still for a little bit. Okay, if all the energy were lost, 100% of it were lost when the collision happened, these cars would be dead in their tracks. They wouldn't move. It would just stop as soon as they hit. Okay, if if these numbers were opposite, right? If 4% of the energy was lost and 96% of the energy remained, then this collision is still going to be very violent, and it almost would look like elastic collision, where they just switch off energies and keep going in a destructive path. Okay, so those are a couple of examples, some pretty good examples to help you out with some collisions.